Hello, everybody. My name is Nicholas Baron. Thanks for joining today for this presentation on Psycho-Acoustics Analysis with nCode VibeSys Using Experimental Data. Before we start, just a few words about me. I used to work for a company that produces fuel tanks, and I used to work in the lab, the acoustical lab of that company, performing measurements for vibrations and acoustics. So I used to measure fuel pumps noise and slosh noise for people familiar with what that is. So the noise that the waves make inside the tank, the fuel tank. All right. So today, what are we going to talk about today? First, we will introduce the concept and the wording and the vocabulary linked to psychoacoustics. Then we will see VibeSys strengths related to that field. And then we will move to the solutions for psychoacoustics that VibeSys provides. Then we will move to the study of a successful case by one of our clients using VibeSys for solving his problems. Then we jump to a short live demo that will show you how to easily build a process to output some psychoacoustics values. And then there will be some room for questions at the end of the presentation. So first, let's start with a few words on HBM Preentia. Who are we? Well, HBM Preentia is a software company, and we have two brands, two families within the company, the nCode and the Rely software brands. We provide also a lot of training and education. We have courses for designed for reliability, durability. We are also rather well known for static theory. And we also provide some services and material testing, especially for fatigue, for example. So the two families, on the left side, on the left column, you have tools for reliability with failure data analysis, test planning, and system modeling. These are Bible, Alta, Blockchain, Reno, RGA, and Lambda Predict. The column in the middle contains tools for the reliability management. So there we want to manage risk, maintenance, and actions. And on the right-hand side, we have the nCode tools for durability. That's the Design Life, CliffWorks for the analysis of measured sinus. Design Life is a CIO-based fatigue analysis solver package. And we have VibeSys, which we will talk a lot about today. And VibeSys focuses on the acoustics and vibration analysis. So today's talk is going to be concentrated really on VibeSys. Okay, all right. So what is psychoacoustics? Well, psychoacoustics is the study of sound perception, or how humans perceive various sounds. Indeed, it is the science of relationship between physical quantities of sound and subjective hearing impressions. Really, this connection between the physical data that you get raw out of an instrument, out of a sensor, and how you will perceive it with your own ears, how, as a human being, you perceive that sound. So the relationship between the two is psychoacoustics. Because indeed, hearing is not a purely mechanical phenomenon of wave propagation. There are nerve pulses that are involved in the process. These nerve pulses, they travel to the brain where they are perceived. So both the ear and the brain are involved in a person's listening experience. So psychoacoustics, we should say that the ear has a nonlinear response, and this is the concept of loudness, which we will talk much later during the presentation. So significant digital signal processing is done by the inner ear. Indeed, the inner ear converts the sound waveforms into neural stimuli. So psychoacoustics also may be used to express the fact that personal expectations might have an effect on the relative evaluation of various sounds. The prejudices, your preconceived ideas on a product will have an effect on how you judge that product, and that is the notion of sound quality. So in the end, all psychoacoustic parameters they provide a linear relationship, a linear representation of human hearing. We will name metrics later, but here I should focus on the fact that a doubling in the psychoacoustic parameters corresponds to a doubling in the subjective perception level you will have, which is not the case with the usual metrics we have in acoustics and that are not specifically dedicated to psychoacoustics. Really, psychoacoustics is the bridge between the raw data and your feeling, your perception of that physical parameter. So really, there is a personal experience involved in that process of judging how nice or how unpleasant a sound can be. All right, so that was for psychoacoustics and the introduction to psychoacoustics. Before we jump, let's talk a little bit about VibeSys, our software, and the key benefits of VibeSys. So VibeSys is brings a very comprehensive set of tools for analyzing your signals. Novice beginners can use VibeSys. It's very easy to start using VibeSys, but at the same time, expert users who have a lot of experience and who need to perform a very advanced analysis can also use VibeSys, because VibeSys really bridges the gap between simple things and complex stuff that you might want to do with your software. You can easily process huge amounts of data, and that's a very strong asset in VibeSys. VibeSys is very capable of dealing with really gigabytes of data without any problem. Another nice aspect of VibeSys is the ability to generate reports automatically and in a very consistent way, so that everybody that uses VibeSys in the company, that uses the same flow, the same process, they will end up having the same kind of report because the process is encapsulated in the flow. So there's a lot of consistency in that. So in the end of the day, hopefully you will save a lot of time and cost thanks to a fast analysis and thanks to meaningful diagnostics that VibeSys will allow you to perform. So the key features of VibeSys. What can you do when using VibeSys? Well, you can study rotating machinery images with things like common waterfalls when the speed is varying. You can get odor extraction, Campbell plots. That's for rotating machinery. Structural dynamics also is a very important aspect for people doing the digital signal processing. In acoustics, you want to have the frequency response function that VibeSys allows you to calculate very easily based on your measurements. You can also do some model analysis, get the resonance, the frequency, resonance frequency, the dampings associated to those frequencies. And that's the structural dynamics part of VibeSys. There's also a vibration manager that will be very helpful for people in the lab dealing with shaker tables, for example. There's a graphical display, as you can see at the bottom here, that really very easily allows you to visualize what your PSD for driving your shaker table will look like, and you can superimpose plots very easily. It's a very nice tool for people in the lab having to run their shaker. VibeSys can analyze gigabytes of data, and really that's very, very nice when you have industrial measurements that generate a great deal of test data. The way you build analysis with VibeSys, that it's the same. You do that in the same way as you do with Design Life or with Glyphox. It's a process and a graphical environment. Meaning there is no coding needed to use VibeSys. You don't need to write any single line of code. You can just connect the blocks and run your analysis just after having connected these blocks. At the same time, if you really need to code, or if you like coding, that's no problem. You can use Python, and you can use MATLAB to integrate your scripts or the things that are not provided, that are not built in the software. So thanks to this Python and MATLAB scripting availability, you can bring your own code into VibeSys and use what you have done in the past. You don't lose what you have done in the past. You can still reuse it within VibeSys. And finally, and that's the talk of today, human perception analysis of human body vibrations and particularly psychoacoustics. That's another subject that VibeSys addresses. So when dealing with human perception, what kind of problems do we address? That could be discomfort, whether it be acoustics or vibrations. It could be issues linked with vibrations, or it could be diagnostics like maintenance, for example. Sound perception. Okay. So what is sound perception? Well, the sound pressure level, which is the quantity that people are usually used to, is a physical quantity measured by the microphone, and that is this value is equally sensitive to sound at all frequencies. There is no discrimination of frequencies in this raw data. But as we said, the human ear doesn't work this way at all. Indeed, the human ear is not equally sensitive to sound at all frequencies. On the contrary, the human ear really discriminates between frequencies. Some are more easily perceived, and some are not easily perceived. And that's the way the human ear works. So a very important thing to have in mind is that loudness is perceived differently at different frequencies. And that's the chart you see on the right side of this page, the so-called equal loudness contours, or some people refer to it as the Fletcher-Manson plot. That's another way to call it. And what does it tell us, this chart on the right side? It tells us that the sound pressure for which a listener perceives a constant loudness depends on the frequency at which this sound is played. In other words, given a constant sound pressure level, the human ear perceives the sound tone as louder and louder as the frequencies are increased up to about 1000 hertz. So you see that really, depending on the frequency of your signal, your ear will perceive it very differently. Indeed, usually for most people, it's between 1000 hertz and 4 kilohertz that your brain, your ear, will perceive sound the best. For lower frequencies and higher frequencies, your brain doesn't hear them so well. And so that's very much probably tells you, this is kind of filtering. Right, and that's true. And that's why we need filters to take into account the fact that the human ear doesn't perceive sound in a linear way, but really in a logarithmic way. And that's the notion of acoustic weighting. Acoustic weighting is applied for human psychoacoustics, and it helps in attenuating the high and low frequencies that we as human beings cannot hear. That's the very well-known A, B, C weighting functions that you will find in most sound level meters. Mostly the A weighting is used nowadays. The B, C, there's even D, it's not written here, but they are fallen some sort of in some kind of disuse nowadays. The prevalently used spectral weighting is the A frequency weighting. So here we have a bridge between VibeSys and these filters, because VibeSys benefits from the Glyphox platform and gives you really a lot of tools for powerful signal processing capabilities, like data cleaning, spike detections, Butterworth filters, fast Fourier filters, all the tools, all the things you need in your bag for doing digital signal processing is provided by Glyphox. So VibeSys and Glyphox, they work together in helping you building your analysis processes. Sound quality analysis, the concept we talked at the beginning of this presentation. Remember, we really, as human beings, have prejudices and preconceived ideas on how we will evaluate and judge some component, and that's the notion of sound quality. So here we have time signals on the left side. It's just it could be a signal from a microphone, just raw data from a microphone, time series data. And the purpose of sound quality is to tell you, okay, we have this raw data, but how enjoyable or how intelligible that sound is. So this is really perception. The metrics and the parameters you need to evaluate this perception of the sound are, as we said, loudness, sharpness, these are spectra, but there are other quantities, articulation index, to name a few. So here at the bottom you see two spectra, one for sharpness on the left side and one for loudness to the right side of the page. So the various metrics that sound quality analysis should provide to help you qualify the item you want, the component you want to develop. Just to name them quickly: articulation index, how many words can you recognize in speech correctly. There is the loudness we talked, and remember this was the chart with the equal loudness contour plots. That's the perceptual measure of the effect of the energy content of sound on the ear. That's, in a simple word, that's sound volume, if you like, loudness. There's also sharpness. Sharpness is, it tells you the sensation caused by high frequency component in a given noise. Really, it's focusing on high frequency energy, sharpness. And there is the usual well-known sound pressure level, whose RMS root mean squared value would tell you also how strong the sound pressure is. All right. So here, these are some spectra obtained directly with with a few of the VibeSys tools, the octave analysis glyph and another glyph. These are on the top. This is the third octave spectrum of the sound pressure that you see, of the raw sound pressure of the raw signal, sorry, that you see on the left side. So displayed in octave, third octave bound. Yes, we have the ability to display them in 12th or 24th octave bands, no problem. At the bottom, you've got in the Fourier transform of the sound pressure level in dBA. See here that the dBA scale unit on the left side of the y-axis. dBA is just for telling you that the A frequency weighting that we talked about a little bit before has been applied to your signal. And you can output also the global level, the so-called LA equivalent. That would be 69.85 for that signal. And also the LAF max, which is the so-called somehow instantaneous maximum value of the sound pressure. F here being for the fast setting of your sound level meter, which is 125 milliseconds. Yeah. So here, people in the lab will recognize these plots in the same way as they are displayed by data acquisition systems during recording. So for people coming from the lab, no worries. VibeSys can also do them very easily, and you will feel at home when doing some post-analysis with VibeSys. All right, so to summarize quickly this introduction to psychoacoustics and human perception, we are compliant with the ISO 2631539 that relate to vibrations. We can do full 24 octave spectra from data in the time domain. We can do PSDs, waterfalls for varying velocity. We have linear dB scales. We have the A, B, C frequency noise filters available for psychoacoustics. We can also calculate the sound level indicators, the usual LA equivalent, the A towers, SEL, etc. We can also replay sound using VibeSys. And also we have some parameters for things that connect to the human body vibrations. And actually that could maybe be the subject of another webinar related to psychoacoustics, these human body vibrations. But for today, we will not talk about that. All right, so let's jump to the second part of this presentation, whose goal was to address and to show you a case study of one of our customers, namely Garrett, formerly Honeywell, who wanted to develop a new turbocharger. So the development of this new turbocharger gave rise to a new type of aero noise source. And in-house, they had no existing methodology to qualify and to evaluate, to assess this kind of noise source. The challenge also was that they had a very short time frame and at the same time a huge amount of data. 65 gigabytes, 54 designs, that's really a lot of data to handle. That amounts to about 30 days of testing. So the first feedback they had is that the usual criteria they had in-house were not good enough for this new turbocharger. So they needed to improve the understanding between this new noise source and the perceived quality, the perceived sound quality of that turbocharger. They used, as you see here, you see the three sensors on the right side. And they use the usual classical 3-microphone methodology for acoustic intensity measurements, which is okay and gives good assessment for constant aero broadband noise source below 4.5 kHz. But this methodology was not well adapted for this new turbocharger that showed a high tonal noise source, constant noise source. It was varying in time, and it also had a very high frequency noise content. So the solutions really that VibeSys provided to them was a lot of flexibility, because they were able to customize their data analysis workflow rather quickly and easily, and also VibeSys was very efficient for them. The workflow they had just been was very reusable, and they can use that workflow on the very many designs they had. 54 designs. That's really a lot of designs to analyze. So just dragging and dropping their recorded data on the flow, they were able to process a huge amount of experimental data in an easy manner. So what did they come to? Well, they developed two new acoustic criteria for qualifying the quality, the sound quality of their new turbocharger. The first of them is what they call fluctuation standard deviation ratio. What is it? Well, it's in the time domain. Here we are on the time domain, and we want to assess so this kind of steam locomotive effect that you would have because of the fluctuation under very low frequency signal modulation. This sound was gathered at the outlet of the compressor through the pulsation sensor. So how did they develop, and what is this criterion? So you filter the sound, you filter the raw signal, and you calculate the standard deviation to better describe the spread description content in the signal. And then you calculate the standard deviation of the original unfiltered raw data to the one that you have just filtered in the time domain. And based on this ratio, thanks to the help of some jury testing, they were able to empirically derive a value, a quantity, a parameter for discriminating pleasant and unpleasant turbochargers. And the value that they found they arrived at was 0.15. If the standard deviation ratio they had calculated was greater than that, you had really present very, very strongly the steam locomotive effect. Whereas when the standard deviation was below that value, people felt and judged that the noise generated was really much more acceptable. So that was the first criterion they had developed, the fluctuation standard deviation ratio. And another criterion they developed is the low frequency peak emergence. This time we are analyzing our data in the frequency domain. So we talk about Spectra here. They wanted to know more the signal, the frequency content distribution of the signal, because the peaks that are more or less visible and more or less white, the peaks emergence was responsible to some sort of, well, how to say that, some whistling feeling when they were listening to the signal. So how did they calculate this new criterion? First, they performed a running average 600 bandwidth window to extract the spectrum overall shape. It's a running average, usual running average, but in frequency domain. Then, very simply, they subtracted that running average to the original spectrum itself. The idea was that doing so, you would really keep only the peaks and the details of the spectrum. And that really helped because even if the overall noise level is low, these peaks, they would really lead to annoying and bad human perception by people listening to this kind of noise. So in doing so, the tonal and the tonal aspect of the signal was really taken into account. And also doing some extensive jury testing, they came to the conclusion that a value of 8 dB for this emergence in the frequency peaks was the value that would differentiate acceptable from non-acceptable turbochargers. Both these criteria, the other one, which was I recall the fluctuation standard deviation ratio, and this low frequency peak emergence, both criteria were validated using a very extensive jury testing. Tens of people were accused, were gathered or participated to this jury testing evaluation to really be sure that the value of 8 dB and the value of 0.15 for the first criterion were really the empirical values that would really help know which turbochargers would be acceptable and which would not be acceptable. So the benefits of this study by Garrett was that thanks to VibeSys, they were able to perform a very efficient and very quick ranking of their turbochargers based on the two criteria which you talked about. That was a very nice thing for them, because from 54, when you have 54 designs, you really need to rank them to be able to know which one you're going to work on in the development stage, or which one really should be left as they are, because they are really there is no chance of having good results with them. The second benefit is that Garrett was able to reduce a great deal the prototype development time thanks to this kind of VibeSys analysis. And finally, which was the main goal of this case study and this development, is that they were able to really know which turbochargers would come with the best sound quality. Remember, this is really something, a perception you want to have. This is not just raw data from your microphones or sensors. You want really to connect, to link any turbocharger to the sound perception it will bring to your customer. So you really need to perform this kind of sound quality analysis to have this kind of result. And they were able to do that very quickly and very efficiently with VibeSys to select these turbochargers that would really be used more more downstream during the development process. So that was possible thanks to the fact that VibeSys is very flexible. It was very easy for the people at Garrett, they told us, to build their own criteria. They really need new criteria, something that was not in the software. So it was very easy for them to build that with VibeSys, to build this new criteria. And that's because VibeSys has all the functions you need for doing digital signal processing in both time and frequency domains. And again, in case VibeSys does not have these tools, there is Python or MATLAB. Just use them. Use coding in case it's not available in the software. So VibeSys is really flexible. Also, VibeSys is very easy, so that building this matrix for them was just a matter of connecting a few blocks, trying, and that's it. Very simple. And lastly, but very importantly too, VibeSys is very fast. And remember, they had gigabytes of data to analyze. That's not something you can do on an Excel spreadsheet, right? You need really a very efficient, and professional software to be able to handle such amount of data. And with VibeSys and with the speed VibeSys provides, that was very fast. They were able to iterate and validate their newly built criteria on big amounts of data very easily, seamlessly. All right. I will not go more into details about that. If in case you're interested to do more about that, just feel free to contact me after the seminar. You will have my contact addresses. Just drop me an email. I will, because I want to leave some room for questions and answers. But before we do that, before we have the questions and answers, let me show you a quick, very basic but quick demo of how you would output some parameters like sharpness or loudness with VibeSys. All right, so let me jump to my VibeSys application. All right. Okay, so here, for people not familiar with VibeSys, this is the main interface, the main page of VibeSys. It's divided into 3 main blocks. On the left side, you have the tree folder here, where you see your data, available data in your working folder. You've got the main workspace in the center here, in the center area. And to the right, you've got all the tools, all the blocks, the glyphs, as we call them in VibeSys. All these blocks that are functionality, mathematical functionality, mathematical functions that are available to you. See here, you've got Butterworth, you've got frequency filter, amplitude distribution. Well, all these blocks are available to you. Just drag and drop them, and you will you have them at your disposal. So let's quickly build a process for analyzing this raw microphone data we have here. So just drag and drop. You have it here. You want to visualize your data. You have zooming. It's very interactive. You can zoom. You've got logarithmic, linear scales. You can zoom and zoom. You can superimpose curves, separate them. Well, that's very interactive VibeSys. But you can also do things in batch if you would like to do so. So here we've got our 2 signals here, 2 microphone signals, and let's output some psychoacoustics matrix. So we will use the sound quality box here. We connect it. Okay, we tell it what we want to output: loudness, sharpness, and pressure level. Okay, that's fine. We tell them we want the spectra. Okay, fine. We want to display them. Okay, so we bring a display glyph. Okay, fine. Let's bring another one. That one on top here. Oh, sorry. Okay. And that's it. You see, I've built up a process for analyzing my data here. Just a couple of dragging and dropping the boxes and connecting them, and that's it. And I'm ready to launch and to run the process. And that's it. You see. So on top here, there's an indicator. You've got the loudness, results, and at the bottom you've got the sharpness results. So you can visualize them, you can separate them. So this is in the usual Borg scale at the bottom, the critical bound rate, and the unit is the sounds per Borg, as is usual with the loudness plots. And for the sharpness, you have the acuum per Borg, again displayed over the critical bound rate here. So that is for the spectrum, first spectrum and the second spectrum, and we could also be interested in the global levels of our signals. So we would just grab them. This is just to show you how to build a simple process with VibeSys. So we go and grab what we're interested in. Okay, some pressure, maybe the sound pressure level, fine. Okay, the sharpness. Okay, and I forgot to add the channel names. Channel title, it would be nice to have that one. Okay, let's bring it to the top. Fine, and we're done. And that's it. You've got the global values of your two microphone signals, the loudness, and sound pressure level, and the sharpness for both the clean tone and the one that had unpleasant sound perception. That's it. And this process is something you could lock, you could save, lock, you could even protect it by password, and you could send to all your co-workers in your company, and they could use that process to analyze their data. So in this manner, in this way of working, they would just have a lot of, just remember the Garrett case, they would have a lot of 54 designs, so they could have 54 files here, and they could just drag and drop these files in the TS input, in that box here, and very quickly and very easily they could build the sharpness and the loudness spectra, and they could compare them very easily.